Hello and Assalamu alaikum everyone. My name is Arsalan Farrukh and I teach math and physics. In this video, I will try and explain to you how to prove the derivatives of sine and cos. If you differentiate sine function, your derivative comes out to be cos function, and if you differentiate cos function, your derivative comes out to be negative sine. So in this video, we will try and explore the reason for that. Somehow this reason is also being derived by a method which is called first principle method. Before we move on towards trying to prove the formula, we will have to identify few things which we will be needing later on, which includes the compound angle formulas, which is if you have sine A plus B or sine A minus B, that simplifies to sine A cos B plus minus, so that means plus pairs with plus and minus pairs with minus, plus minus cos A sine B. Similarly, cos A plus minus B opens up as cos A cos B minus plus sine A sine B. Also, I have done a video where we have derived these compound angle formulas, and I will put the link in the description of that particular video. Plus, you also must know that sine functions and cos functions are the periodic functions, that is, they repeat themselves after every 360 degrees or 2 pi radians. So for one cycle, this is how a sine function looks like, and for one cycle, this is how a cos function would look like. So this is one cycle of sines, which also means that if I continue drawing this graph, it will just keep on repeating itself. And similarly, if I continue drawing this graph, it will also keep on repeating itself. Also, you must know two identities. One is that if you have limit delta x approaching 0, that is delta x is very, very small, then sine of delta x divided by delta x almost is equal to 1. So what we are saying is that if you keep on moving towards 0, then the value of sine theta and theta are approximately equal to each other. Please bear in mind that this is only applicable in the radian mode. You can sort of try and visualize this by means of a right angle triangle, and you can see that if this angle is theta, then sine theta is going to be perpendicular upon hypotenuse. And if you will look at this as approximately a sector of a circle, then you can also say that P is equal to h theta, or P upon h is equal to theta. So it's just an approximation. We are talking about very, very small angle, but somehow what we need to sort of identify is that if the angle becomes really small, then sine theta value matches the theta value. You can also verify this by using calculator. You put your calculator in a calculator mode and take out a sine of something very, very small. So you'll see that this will come out to be approximately equal to 0.1. It's actually going to come out as 0.0999, which is almost equal. So this is obviously just an approximation. So if you keep on making this angle smaller and smaller, the identity is gonna keep on becoming more and more applicable. Well, and the most important thing is that we have to recognize that this is one identity that we will be using, that in radian modes, if this angle is nearly equal to 0, then sine theta divided by theta is approximately equal to 1. Similarly, if the angle is really, really small, you can see that for very, very small angle, the value of cos theta is approximately 1. So for this to be approaching 0, this will approach 1, and this 1 minus 1 will approach 0. So the other identity that we will be using is that if delta x is approaching 0, then cos delta x minus 1 approaches 0. Lastly, you have to recall that what is the gradient function. Basically, if you have a graph and you want to find out its rate of change, then the gradient basically represents the rate of change. So if you have a straight line segment, the gradient would just simply be delta y divided by delta x. But then you realize that if it's a nonlinear function represented by a curve, then its gradient is not constant. So you can't simply apply this direct formula, and hence the gradient, since it's not constant, it is called gradient function. So gradient function is obtained by taking out d delta y over delta x for a very small portion or a very small segment of the curve where it approximately matches the gradient of the tangent to the curve at that point. So at different points it has different gradients, and hence we get, instead of a constant value gradient, we get a gradient function. Gradient function that we represent by dy by dx is basically delta y over delta x for delta x to be nearly approaching 0. Well, getting to know these things, let's move on towards how we get to the formula of derivative. So if I want to find out the gradient function of y is equal to sine x, what I'm going to do is that I'm going to take a point with a small change in y and a small change in x, and I will say that just that y and x would satisfy the equation, y plus delta y and x plus delta x would also satisfy the equation. So in place of y, I wrote y plus delta y, and in place of x, I wrote x plus delta x. Don't forget, you're looking to find out delta y over delta x with the limit that delta x is approaching 0. So what you're going to do is that you're going to sort of try and rearrange this equation into this form. Clearly, I'm going to have to move this y on the other side, plus I can see a compound angle formula applicable here. So sine A plus B is sine A cos B plus cos A sine B. In this case, it is going to be sine x cos delta x plus cos x sine delta x. In the next step, I move y on the other side. Do not forget that this y is basically equal to sine x. So in place of y, you can write down sine x. And then after that, you can sort of rearrange the equation and move this sine x over here. Purpose being that I can take sine x common from these two terms. So I will be left with cos delta x minus 1, and this will be just simply cos x sine delta x. Now, this is delta y, and I was looking to find out delta y over delta x. So I have divided the entire equation by delta x. So once I divide the entire equation by delta x, now I can see that this is where I can apply one identity, that if I apply a limit onto it, which is limit delta x approaching 0 and delta y over delta x is what I'm trying to find out. So I would say that this sine x divided by delta x is getting multiplied by this, where cos delta x is approaching 1 for a very small delta x, and cos delta x minus 1 is approximated as 0. So what I can do is that I can multiply it by 0. You might probably think that there is a delta x over here, and if delta x is approaching 0, why don't you put 0 over here? Well, the reason being that it's approaching 0. Do not forget that it's approximately equal to 0, but the fact remains that it is not exactly equal to 0. So wherever I need, I can replace it by 0, where I know that's a very small value, but otherwise you know that this is not exactly going to be 0 and it's going to be something really small. And then I have a plus cos x multiplied by sine delta x upon x, delta x, sine delta x upon delta x, and about which we also identified earlier on that for very small angle, sine delta x over delta x approaches 1. So in place of this, I can write down 1. And if this is dy by dx, I get myself the formula for the derivative, which is going to be cos x. Now, this is like the entire mathematical approach, but you can also look at one more thing, that if you look at it graphically, this is your graph of sine x. And if you look at its initial position, you would identify that the gradient is positive. So there must be some positive value of the gradient. But if you look at this particular point, you would recognize that the gradient becomes 0. So at this point, the gradient has a 0 value. So I can, if I just try putting down the values of gradient over here, I can see over here as well that the gradient is negative. So the value of gradient is going to be negative. So I put down some negative value for the gradient over here. Then I can again see that over here, the gradient is 0. So if I'm sketching the gradient would be 0 over here, and then I would recognize that over here, the gradient has again become a positive. So if I will try and trace up these points, you might be able to figure out that this is forming a pattern, which is a cos function. So that sort of also graphically explains that if your original function is y, then its gradient function or its rate of change is going to be cos. Moving on with the next example, we have a function which is cos x. We will take the similar approach. We will try and find out the gradient function of cos x. For that, we will suppose, just like there's a point xy onto it, we will suppose that there's another point which is x plus delta x and y plus delta y that satisfies this particular equation. And hence, in place of x, I can write down x plus delta x, and in place of y, I can write down y plus delta y. After having done that, I will again try to make delta y the subject of the equation, and to be able to achieve that, I've put y on the other side. So I've shifted y over here, and after shifting y over here, I will again recall that y basically is equal to what? Cos x. So I can replace y as cos x, rearranging these two terms together. So these two terms are being put up together. This term is over here, and then lastly, what I'm doing is that I'm dividing it by delta x, bearing in mind that my entire approach is towards finding out delta y over delta x for delta x to be very small, which gives me the gradient function. So after dividing this entire thing by delta x, I can again sort of, taking cos x common, I can recognize that for very small angle, cos delta x approaches 1. And if this approaches 1, then 1 minus 1 approaches 0. So this entire term is going to become 0. And another identity that we did talk about, which is just, these two are just approximations, do not forget that. But sine delta x upon delta x would be approximately equal to 1. Which means that when I will apply these concepts, that is, I'm going to put limit delta x approaching 0, delta y over delta x. So this is going to become cos x over delta x times 0 minus sine x times 1. This thing, which is limit delta y over delta x, we write it down as the gradient function and we represent it as dy by dx. So it's basically the same thing. The only difference between delta y and dy and delta x and dx is that delta y is any change in x, but dy is a very small change in x. And similarly, delta x is any change in x, but dx is a very small change in x. So I get myself dy by dx, and that's coming out to be negative sine x. So this tells me that mathematically, if the original function is cos x, then its gradient function is going to be negative sine x. I can also look at it graphically, which is, you must know by now, I told you in the beginning, that this is how the graph of cos x looks like. So if I want to sketch the graph of dy by dx, I would be able to recognize that initially the gradient is a horizontal flat line, which means the gradient is going to be 0. And then over here, the gradient is negative. So I will put down some negative value for the gradient over here. And then at this point, the gradient becomes 0. And then at this point, the gradient is positive. And at this point, the gradient again becomes 0. So putting all of this up together, I would know that this is how the graph looks like. And if I will try and connect these points, this basically forms the exact reflection of the original graph of sine x. So if this is how the sine x looks like, which I told you initially, this must be negative sine x, which tells me that the gradient function must be negative sine x. So we have like sort of a mathematical evidence for that, and then some sort of graphical backing to support our claim. And this is how we get ourselves the formula for the differentiation of sine x and cos x. I hope this video made you understood how we apply first principle method to get ourselves the derivative of sine x and cos x. If you did like this video, please give a thumbs up and also share and subscribe to the channel. Thank you.